Hola amigos! Welcome to the second chapter in this tutorial series. Today we're going to resume right where we left last time and add more details to our lightning ball effect. On the lightning itself, the most visible change is the addition of secondary lightning arcs, but we'll also improve the ribbon material since we're using it multiple times. This material has more detail and it splits its RGB channels before fading out, creating the illusion of a lens distortion. We're adding a few smaller details as well, like some diffraction lines around the impact points and some small clusters of lightning coming off the sphere. When combined, all these small details will make the effect look a lot more interesting. Speaking of the sphere, we are going to give it a new material with a chaotic vertex deformation and add more arcs of lightning orbiting it. As you can see, we have lots of pieces to add today, but almost everything is going to be pretty similar to the stuff that we covered in the first video. This time, I will cut some of the menu clicking and stuff like that, and slow down only on new concepts or techniques. And without further ado, let's get started. And this is the scene as we left it last week. The sphere is shooting some lightning bolts, but not much else. We're going to start with the ribbon material, since this is the single most used asset for now. Here it is. I know, it looks a bit more complicated than before, but it's still quite straightforward. The emissive color is just the multiplication of the particle color by a vector made by sampling this texture 3 times, once for each channel. This is a rather simple texture that I made in Photoshop and that you can download for free from the link in the description below. As I said, I'm sampling this image 3 different times, but their UVs are slightly offset for 2 of the samplers. Since it is a grayscale texture, we can take any of their components to create a new vector, using the MakeFloat3 node. These offsets have the same value in both cases, but we are adding the value to the UVs for one sampler and subtracting them for the other. That means that if this value is greater than 0, the red channel will shift towards the bottom right and the blue channel in the opposite direction. For this effect, the offset amount will be controlled by a dynamic parameter that we can easily set from the Niagara system. We're going to use it to add a bit of chromatic aberration to the lightning at the beginning and end of its life. This is gonna be a subtle effect, but in my opinion, these small details are quite often what separates good visual effects from great ones. Note that since we're using the UV coordinate space, which goes from 0 to 1, the offsets that we'll use will have to be minuscule. Even a small value like 0.2 will make the channels split completely, which is too much for this effect, as you can see here. The other part of the material is the opacity output, which I'm simplifying by taking only one of the samplers and multiplying it by the particle alpha. But you should consider improving it by adding the 3 values together and then clamping the result between 0 and 1 with a saturate node. Another improvement, which you could say it is homework to do before the next tutorial drops, would be to add a bit of refraction to this material, masked by the texture and controlled by the green channel of this dynamic parameter. Speaking of this dynamic parameter, let's go to the lighting Niagara system to make use of it. The Dynamic Material Parameters module is the easiest way to communicate between Niagara systems and the materials that they are using. We can use up to 4 different parameters, each one of them with 4 channels, RGBA, giving us a total of 16 variables that we can share. The module is smart enough to tell you which of these parameters are being used in the material currently. And as you can see, I've already set this one to scale down the first channel to 0 at the beginning and then to 1 at the end. The scale of this curve is set to 0.05, which will add a tiny but visible amount of chromatic aberration on the lighting. Let's check it out. I'll go frame by frame so we can zoom in and take a moment to see what's happening in detail. Here, like I said, the effect is very subtle, but the brain still registers these few frames of color distortion that help sell the idea that these arcs are so bright that they affect the camera sensor. In the future, we will add a similar full screen effect with a post-process material, but that will come in due time. Next, we'll add a light to the effects blueprint and start setting the variables that we'll need for the branching arcs. Let's start with the light. Most of its parameters are very straightforward, and I'm sure that most of you are already familiar with them. It is just a point light with source radius set to approximately match the sphere and add a soft blue light around it. A key aspect of this light is the high volumetric scattering intensity value, which is set to 25. If you have a fog source in the scene, which by default there is, and set it to volumetric, this setting on the light will add a great looking glow to our effect. We could achieve this with cars too, but once we start adding destruction elements to cast shadows inside this volume, you will appreciate doing it this way instead. Give me a moment to turn the lights on. Perfect. Note that the intensity and attenuation settings will also affect the brightness of the volumetric fog around the sphere. In this case, I set a high scattering value to get a good amount of fog glow without overpowering the light's intensity and killing the rest of the effects. Like Thanos would say, balance is fundamental. Let's work on the branching lining next. I've already created 3 new local variables that will set right at the end of the graph. These variables will save the location of the last hit including the offset, and the last impact normal values, and pass them over to the next copy of the effect. I've also added a couple more variables, a boolean and an integer, to control if we want branches and how many if so. The last new variable is a float, which will be used in a moment to get a new random direction from the original one. But before we put these new variables into use, let me show you the new effect that we will use for the secondary arcs. I've made a duplicate of the original Niagara system and removed the lingering particles emitter from it. I've also reduced the sprite and ribbon sizes, brightness and amount of particles. The last change that I made in all the 3 emitters here was to set a small loop delay, just a tiny fraction of a second, to have the secondary arcs start a frame or 2 after the first ones. Other than those small changes, the system is identical to the main one. We want the lightning bolts to look consistent, just make these ones a bit less intense. And now, with an effect that we can spawn, it's time to head back to the blueprint to start firing some lane traces. Here is where I thought that I would make things easier to see by adding a sequence node here at the beginning to add the second traces. But the most observant of you probably have spotted the problem with that. We want the second arcs to come from the first ones, but only when those hit anything. This means that the sequence should be put after the branch where we check if there was a hit. Don't worry, that myth from the past will notice the error in a few minutes and fix it, but you can save a few clicks by placing it in the correct spot now, between the branch and the spawn Niagara system nodes. This part is still correct though. First, I'm adding a new branch to check if we want secondary lining, and then a for loop going from 1 to the maximum number of arcs that we want. We're using the breakable loop variant because we'll interrupt it in case the secondary trace fails to hit anything. This is the new line trace. Let me explain with a little graph. For the origin, we'll take the location of the last hit and offset it in the direction of the normal by a certain amount. Then, we'll pick a new random direction in a cone aligned with the previous one and project that from the origin. When we set the new lighting effect parameters, we will make it go from the last hit location to the new one from this line trace. Oh, by the way, here's where I noticed my own mistake with the sequence from earlier and moved it to the correct location, right before we spawned the first lightning arc. I also added a comment box around this group to make things easier to read. With the error fixed, we can repeat the steps from the main lightning arc, first breaking the head result and spawning the new system if there was a collision. Since we have those nodes over there, I'll just copy-paste that section of the graph and redo the connections. This time, I'll connect also the false output of the branch to stop the for loop when a trace fails to hit a valid surface. After adding a pair of reroute nodes to clean up the graph, we can replace the Niagara system to spawn with our new simplified duplicate and start populating its variables. The first variable, beam start point, is set to the location of the last hit, including the offset. The second one, beam end point, is set to the location of the new hit, plus a small offset to avoid set fighting issues with the sprites, like we did before. We can copy those nodes from the first system spawn and paste them here. The last variable of this Niagara system can be directly connected to the impact normal of the hit result. Here I noticed that when I copied the set variable and spawn system nodes, I missed the default scene root component reference, so let me fix that and also copy the bit where we save the variables from the last hit, so we can do the same here to update their values. By the way, both primary and secondary arcs can be done in a single loop. You just need to check the loop index to know if you want to spawn the primary or the secondary arc effects. You can even pass that variable to Niagara system and have a single emitter that scales down its parameters using that same value. I might make those changes off camera later, but for the purposes of this tutorial, I will keep the simple version. After giving all these new variables a default value, we can give this a try. Excellent, everything seems to be working as it should. The new arcs look pretty cool and add a lot of visual interest to the effect without taking over the main bolt, despite being up to 3 of them. In addition to scaling down the effect with each jump, another thing that you can try is branching some of them by sometimes tracing twice in different random directions. Or, if this was an in-game player effect, check the material of the surface hit and create secondary arcs only on metallic or water surfaces to create some interesting gameplay combinations. Next, we're going to add 2 more detail layers to the main lining arcs. The first one is a small burst of diffraction lines, done by spawning a single sprite quad facing the camera in this new emitter. This one is the simplest so far. It emits one single particle, places it at the hit location, and scales it up and fades it down over time. No forces or anything else, this is just a small detail to add a bit of color around those points without adding too much brightness at the same time. The material I'm using is also very basic. I'm only sampling one texture and multiplying it by the particle color for emissive and using the particle alpha directly as opacity. Since this material is painted with additive blending, we don't need to be precise with its transparency. And like before, I've also included links to download this diffraction line texture and a variation of it. These are the only textures that I'm using that are not present in the Unreal content folders. Let's give this a try and see if I can pause this to catch one of these textures as it is doing its thing. Here, like many of these other complementary effects, these are subtle but still visible, which helps fill in those small gaps that maybe you don't notice at first, but your brain does. If you're following the tutorial along, maybe you can try emitting a second particle sprite a moment later, or adding a bit of noise to the color scale to match the brightness changes of the bolt, but I would be careful not to make this too visible. The final layer that I want to add to the main lining effect are a couple of tiny sparks sometimes coming off the sphere when there's a hit. This emitter is also quite simple. It loops once, with a longer delay than the others, and then has 2 different instantaneous spawn bursts, with a short delay between them as well. I lower the spawn probability of these bursts to 0.75 in the first one and 0.25 in the second, so they don't occur every time. The reason for the 2 separate bursts is that I'm assigning each one a different ribbon ID based on the spawn group property, so the renderer doesn't connect both of them together. Note that you will need to assign a spawn group number manually. If you cannot see the property in the module, click the down arrow in the panel to show the advanced properties. Once we give each group of particles their own ribbon ID, the rest of this emitter is pretty straightforward. A bit of reverse gravity to make them float upwards, a bit of jitter to make them look chaotic, and an inherit velocity module set to very small values to slightly follow along the parent sphere's movement. In this emitter, I also added a curve to control the jitter amount and take it down at the beginning and end of the particle's lifetime. Since we are not being precise with these curves as we've been with the rest of the lining, I thought that this was an easy way to give these sparks a bit more interesting motion. I'm using the same material as well. Something I forgot to mention is that if you're using the tile by segment length UV mode in these emitters, you will have to adjust the tiling length on each of them to get the best results. Let's try playing the effect and see if you can spot these small clusters of lighting trailing behind the sphere. I think they work. Maybe you can play with the color settings and scaling curves to make them a bit less monochromatic, but in general I think this is a great start. And now we can move on to the sphere material and replace the boring default one with something much more alive. It looks complicated, but we are only using two outputs, emissive and position offset, so it's not too bad. The material itself is unlit, two-sided and uses additive blending mode. Let's look at the emissive color first. We have two sets of texture coordinates with different tiling settings, followed by panner nodes that move them over time. Afterwards, the red and green components of the bottom sampler output are scaled down and added to the UV coordinates for the top sampler. Let's preview this second texture sampler to see what we end up with. As you can see, the combined panning of the first texture with the distortion added by the second one produces very chaotic results. I'm not scaling down the speed because this seems more or less appropriate for the effect that I have in mind. By the way, these textures are available in the Unreal content folders, so there's no need to download them. You can also experiment using the rest of the different available noises, but remember to use a color one for the distortion, otherwise the red and green channels will be the same. The final step for the emissive output is multiply this by a color parameter, which I set to a bright pale blue to pair with the rest of the effects. Let's take a look at the wall position offset now. I'm taking the grayscale output from the sampler and first multiplying it by a parameter, then subtracting another from it. These two operations will scale and bias the result. Next, we're multiplying this another two times. First, by the sine of the time to make it oscillate between the minimum and maximum values, and then multiplying it by the vertex normal in world space. Using this as the position offset will make the vertices of the sphere pulse in and out at a constant rate, which will be enough to bring some of this chaotic electric motion to the mesh. You can tweak the scale and bias parameters to adjust the size of these spikes and how much of the motion goes inwards versus outwards. Since the sphere I'm using for this tutorial is pretty small, I'll keep the scale to a low value. Next, let's apply this new material to the mesh and see how it looks in the scene. Great. Finally our sphere looks a bit more believable as the source of all this lighting, but I think that we can still do better. Next, we'll add a bit of detail to it with some lighting arcs orbiting its surface. We'll create a new Niagara system for this effect, and we will attach it later to the sphere in the projectile blueprint. Let's check it out. This emitter creates some particles with unlimited lifespan and then arranges them into this spinning double orbit pattern. Here's how it works. I'm using a GPU system because later on we'll spawn a lot of particles from it to make a second trail, and at that scales, a GPU system will be always more efficient. In the initialize particle module, most of the properties are either unset or set to simple constant values. Next, the Kill particles when lifetime has elapsed checkbox is disabled because we want these particles to live forever. As you can see, this is all very standard. The key part happens in this setPosition module, where we are going to use a bunch of math to play the particles in very precise locations. In this case, I'm going to do it manually with Niagara pre-built modules, but if you collapse those, you will get a condensed version of this in expression form. Note that this expression is missing the scaling and bias factors that I will use, but if you want to, you can almost replace all the stuff that I'm going to explain next with this line of code. The components of this vector are made all the same by taking the sine or cosine of the emitter h plus the normalized execution index. The sine result is then scaled by a local parameter that controls the radius of the orbit. The normalized execution index can also be scaled, which will distribute the particles along that number of orbits. For example, a value of 2 will distribute the particles twice along that orbit in an axis, while a value of 0.5 will only cover half of the orbit. You can play with these values to achieve different effects, or swap sine by cosine in one of the axes. Here are the parameters that I'm using to get this pattern. The scale of the index is 2 on the x and y axis and 1 on z. I don't think there is a correct way to do this. I found that I liked many of the patterns that I was getting while changing these values. You can even combine multiple distribution patterns together to get more complicated effects. Anyway, the rest of this emitter is quite simple. There is a ribbon renderer using the same material that we've applied to all of our lining effects, and a bit of jitter motion to make it more chaotic. After that, the only thing remaining is to go back to the blueprint and attach one of these to the root component so we can see it in action. Here's a neat thing. If you have the Niagara system selected in a content drawer, Unreal will automatically use it when you add a Niagara component to a blueprint. Here's the updated effect. Maybe I can lower the orbit radius and increase the thickness a bit, but other than some minor tweaks, I think this is looking pretty good, which means that we can move on to the last effect for today's video. In this case, I'll add a new emitter to this last system, since we're going to create a trail from these orbiting arcs. Okay, here's the emitter. This is going to be a subtle, wispy trail left by the sphere as it moves. We don't want to make it too bright. Most of the emitter is pretty conventional. We're using the spawn and sample particles from other emitter modules, which you should be familiar with if you have followed some of my previous tutorials. I'm also setting the spawn count quite high. This is the reason to use a GPU system. Otherwise, this large number could crash some video graphics cards. The motion is mostly coming from a curl noise force, but the most interesting aspect of it is that the drag value scales over time, to have the particles quickly accumulate when affected by the forces, but gaining drag over their lifetime so they move less and less as they fade. I think that this emphasizes the tendrils of the effect without making it look like every other curl noise particle pattern out there. And with these last steps, we can finish the video and mark this tutorial as complete. Today we've added a few layers to this effect, most of them quite simple individually, but I think that they contribute a lot to the overall finish of the lining. In the next tutorial, we'll start breaking things down, using some pre-animated destruction assets that I'm working on right now, and maybe adding another trail effect. If you stayed until the end, thank you for watching this video. If you like the content and want to stay tuned for the next chapter in this series, don't forget to subscribe and click the notification button below. See you next time!